A little bit more about torque today. So what is torque? An angular momentum, actually. So, excuse me. For a single mass, right? So we got to pick an origin somewhere. So here's the origin. So with respect to that coordinate system, that mass has some position vector r, right? So, like so. And then of course the mass has some velocity v, right? So you can calculate the torque on that mass. Now the torque is a measure of twisting motion of the mass around the origin in some sense. So suppose the net force is something like this. I don't know. It could be any old direction. It doesn't really matter. The torque on the mass is equal to r cross f by definition. Now, I give you reasons that that's a good definition as it relates to rotational motion. The other days we talked about it, but there it is. That's the definition for this. Torque is the radius across the force. Now we can ask questions like, what's the significance of this? What's this have to do with, for example, angular momentum? Angular momentum, we've also defined, you can also define in terms of quantities we're considering here. Angular momentum, L, is equal to r cross the linear momentum, P. So, but P, remember, P is the momentum, P was what? P was mv, right? So this is r cross mass times velocity, or if you like, mass times r cross the velocity, like that, angular momentum. So we can try to understand how does the torque relate to the angular momentum, right? So a simple calculation will show us the relation. We can calculate dl dt here. So let's go ahead and do that. What happens when you differentiate a cross product? So I'm gonna go ahead and pull the m out and the m. So m is constant, right? So I can pull the derivative through that. So I have ddt of r cross v. Right. And so the product rule tells me what? This is m times dr dt cross v plus r cross dv dt. Now, what is dr dt though? Well, dr dt is exactly the velocity, right? The instantaneous change in the position with respect to time. So what we're really looking at there in the first term, right? Let me circle it. This right here, what is this?
Velocity squared.
Velocity squared. It's worse than that though. It's velocity cross velocity. Remember, the cross product gives you a vector which is perpendicular. It's in some sense a measure of the perpendicularity of two vectors at least. You know, the larger the cross product, the more perpendicular the two vectors are, right? So when two vectors are the same, the cross product is zero. So that term is zero. And so the other one, let me bring the m back inside now. That's r cross m. And this dv dt I could call what? That's just a, right? The acceleration. So r cross ma, well, what's ma equal to by Newton's second law? Force, right? That's force. So what we have is r cross f. And what is that? It's a torque. So as you can see, we have just derived that the time derivative of the angular momentum is equal to the torque. So in particular, what happens if the torque is zero? Well, you say, well, then dl dt t is equal to 0. What's that mean? It's what? R and F are in the same direction. Well, it could be that. It could be they're in opposite directions. Could be one of them 0. So those things can happen. How about this? If I have L sub 0 at time 0, and I have L sub F at time F, right, at the final time, how are these related? In the case the torque is 0.
Same.
They're the same, right? So in other words, the angular momentum does not change. So if the torque is 0, we have conservation of angular momentum. Just like before, we had, if the force was 0, the net force was 0, we had conservation of linear momentum, right? Now, I showed you the derivation for a single particle, but you can easily extend this to a system of n particles. I'll show you that here. Funny how it doesn't work unless you plug it in. Okay. So some of you look different. Like show of hands, who's C5 here? Oh my goodness. You're not C5. That's right. So how many are there? 1, 2, 3, 4, 5, 6. Any over here that I missed? No? Okay. Oh, they know enough to not sit by that trash can back there. There's reasons. I may have thrown an egg in there the other day. Probably rotting by now. It's probably gone. More fun to think it's still here, though.
Yeah. I came really like to should have come to some biology lab yesterday where we used gels made of sulfur.
Oh. So this is, technically speaking, my lecture 30 for you CFOP people. If you really want to look at this later, you can go to my website, which incidentally is www.supermath.info. On that website, I have PDFs of all the courses I teach. There are a few. I don't know how many courses have I taught here.
You also have a copy of your doctoral thesis.
Oh yeah, that's it. I should get that. So anyway, suppose you have n masses, all right, and you can suppose that they have external torques, tau 1 through tau n, placed on them. And then you can think about the forces that the masses put on each other, right? Like we could think of these n masses as being like you guys. And imagine that you're all playing like tug of war with each other with like little ropes, right? So there's lots and lots of like internal forces that would be those tug of war forces. There's that, there's that one. Some of them. Oh, okay. So, you know, all those internal forces would be like these tau oj's. So the internal forces would give rise to internal torques, right? But the thing about, for example, the internal torques is that the torque that I puts on J is actually going to end up being minus the torque that J puts on I. Well, at least that's true to the force by Newton's third law, that there's an equal and opposite reaction. So the force you guys put on each other have to come in third law force pairs, and that turns out to make this contribution go to 0. Here's how. So the net torque would be the sum of the torques, the external torques, and the internal torques. But the internal torques, you could say I less than J, I greater than J, I equals to J. Well, you torque yourself. Can't do it. It's not possible. Because you are where you are, so you can't put a torque on where you are. Oh, anyway, so
If I was a cat.
if you were a cat, we'd say you'd 0. So anyway, you have these terms and these terms. Through a sneaky trick, I exchange I and J. So I relabel this sum. Think about this. If I change this to I less than J, I just have to flip these and they're the same things added up. But then you can factor out the R sub I. and you're left with Fij plus Fji, but that's 0 by Newton's third law. And so you can see the total torque that you get on a system of things is just the sum of the external torques, which then tells us that we have conservation of angular momentum for a closed system. If you have not a closed system. If you have a system, you can, and such that the net torque on it is 0, then you have conservation of angular momentum for such a system. Here's an example. Suppose you got like a disk spinning around with angular velocity omega. It could be like a, I don't know, it could be like a merry-go-round wheel, something like that, right? You don't see those so much anymore, right? So let's say you go and run onto and jump, and they go around in circles.
They're too dangerous.
They're fun.
Are they too dangerous, or
Might get hurt.
They probably are. There's something moving. Like,
yeah, moving at playground is dangerous.
You might hit your head.
And they're always made out of metal things, so.
You know, if you can't get hurt, you're not getting free.
oh,
Yeah.
exactly.
So, you can think about this as a kind of closed system. You have the mass before and after. Mass drops, sticks onto this wheel, which is turning, right? And then suppose it sticks on. Now, if you look at this, the only thing that's, what make the mass, whatever made the mass drop, gravity, that's not going to directly put a torque on the system. It's, well, because the gravity is perpendicular to the rotation of the disk. So, anyway, let's throw that. So then the question is it going to slow down? Is it going to speed up? What happens? I mean, it slows down, right? If another kid just jumps onto the merry-go-round while it's spinning around, it's going to slow it down as soon as he jumps on, right? Now we can do this directly, because the other thing I haven't mentioned today yet, but remember we worked out the other day, is that the angular momentum is equal to the moment of inertia times omega. At least if the spinning is along the axis, right? So I can basically calculate the moment of inertia to start with. So I told you that the disk has inertia I1. And then, although I can quantify that, that's 1/2 mr squared, right? Because the radius is r, and the mass of the, I need a mass of the disk. If the mass of the disk was m to v, then I for the disk would be 1/2 mass of the disk, r squared. And so we can use conservation of angular momentum here to figure out how fast it goes after it sticks, right? So here's how that goes. Initial angular momentum equals final angular momentum, so I have the moment of inertia for just the disk. And when the mass is just there to start with, even right before it's dropped, you can think about it this way. So you have the disk spinning, right? And you can really consider the case right before it hits the disk, like right here. So the mass is falling downward, right? So if you think about the disk, think about the disk and its motion, it's like this, right? So the mass right here would be falling downward like that, right? So if you look at that, and if you look at the radius around the rotation, you can see that the velocity is actually not in the right direction to have angular momentum, right? It's the angular momentum should be it doesn't add angular momentum to the direction of the spinning, at least. There's a different kind of angular momentum it has, but we're ignoring that in the sense that I'm not supposing that the mass drops onto the disk and it starts wobbling because of the weight of the mass dropping. We're essentially ignoring that vertical impact in this problem. We're just paying attention to how it's going to slow down the rotation, right? So I omega is equal to I1 omega f. I don't know what omega f is yet, I'm trying to figure that out. And then there's also the inertia of the mass which is dropped, right? And we could suppose that the mass is a cat, if you like, I don't know, whatever. Maybe a dead cat, because I'm assuming it sticks to the disk, so probably the cat's dead. It could be or if you see a cat covered in like tar or something, yeah, sure. Oh, maybe peanut butter, maybe, I don't know. And so, Sure, or here or there. So anyway, then if you look at this, there's only one thing I don't know, which is what I'm interested in, which is omega sub f, and I do algebra. Solve for it. So guys, for those of you who are wanting to give useful advice to the CFARs, what matters more here, algebra or calculus?
Algebra.
What?
Algebra.
Algebra. Yes, algebra is the correct answer to that question. Math is what matters. That's also true. Yeah. So if you compare the kinetic energy before and after, you'll find you have less kinetic energy after, more before, because this is a sticky collision, right? Which is, even in the rotational case, still an inelastic collision. So here's another one. Suppose a child jumps onto a merry-go-round. The disk radius r with mass m. If the disk spins horizontally, the child has a mass m and jumps onto the point like 4/5 of the way out from the center, tangential velocity v. Find the omega sub f for the child and merry-go-round together. So I'm assuming initially that the merry-go-round thing is not spinning. So basically you have the child run up, jump onto the thing, and then it starts spinning as a consequence of him jumping on. The question is how fast is it going to spin, right? So again, this is a situation where there's no external torques. Basically, you have the angular momentum of the child right before he hits the thing and right after the child merry-go-round system. So again, we can use Li equals Lf. The moment of inertia for the merry-go-round disk is 0 to start with. The moment, the angular momentum of the person right before the kid jumps on would be m times 4r over 5, because that's the distance, that's the r, and the mrv for L. And then that will be equal to the moment of inertia afterwards. The moment of inertia afterwards is this, 1/2 mr squared for the disk, for the merry-go-round disk. And this will be the moment of inertia for the child, which is m times 4/5 r squared. It's just the mr squared formula, because the distance is 4/5 r. So that, and then this we don't know yet. And again, we do algebra. And there we go. That's the angular velocity that you would have as a consequence of that.
So the merry-go-round starts at rest.
Yeah. Now, if the merry-go-round did not start at rest, all that would change is you put the initial angular velocity here, right? And of course, it would be more challenging for the child to jump on, but we don't really care about that. I say see Tipler for further examples, but that is somewhat misguided advice since we haven't been using Tipler for about 3 years. So sorry about that. Tipler's a good book, though. But so is your book. So. Oh, what's this all about? I don't really want to talk about that today. I'll put this away. So, any questions? Well, this is Friday. As you know, physics always gets out after 15 minutes on Friday. So, actually, I'm sick, so I'm going to stop talking so that I will talk next week for you CFARs. If you have any questions about anything, I'll be here for a couple minutes if you have what I need. So, the rest of you, why are you still here? Gone with you. Next week, we'll start gravity.
The movie or that concept?
Gravity? No, not the movie. The movie. You're not my enemy. I don't want to punish you.
Wait, did you see Interstellar though?
Gravity is a horrible movie.
Thank you.
Oh, terrible movie.
It was her breathing in space for like 2 hours.
Breathe in space, right?